Okay, let's get started. So today, after review, after recapping what we learned in the last lecture, we have a quiz. Okay, about 12:15 or 12:20, we'll start the quiz. Okay, so can you first check it? Okay, microphone is working. Okay, so this is the outline for today. First, we're gonna review what we learned in the last lecture. In the last lecture, we learned mainly two topics. One is off-policy prediction and control with approximation. Another one is eligibility traces, which is the progress of the last lecture. And today we're going to learn a new topic, which is policy gradient methods. So this topic is very kind of a new topic, and also most recent research results and reinforcement learning approaches, method, and the framework are based on this policy gradient method. Okay, today we're gonna very carefully study this policy gradient method. Okay. So first we're gonna review what we learned in the last lecture. The first one is off-policy control with approximation. For this topic, as you remember, I just go through those major algorithms development. I didn't go to detail, very detailed, because those actually you can just combine the off-policy, what we learned in the previous, the value-based, the tabular-based methods with the approximation together. So based on this concept, we developed several like methods like episodic semi-gradient step salsa, and average reward. Okay, so now later we learned these eligibility traces. Okay, the first one, this off-policy prediction and control with approximation. As I mentioned, we can just combine what we learned previously with the off-policy strategies. Like we can use the IS, important sampling ratio, to rescale the error, TD error. In this case, we use the TD0, the one-step TD error to rescale. So we have two settings, because previously we already learned the episodic and discounted and continuing and undiscounted. So for these two cases, actually we have different TD errors. Okay, with these two TD errors, we can update the weight vector. After that, we also learned the semi-gradient expected salsa without IS. So we kind of extended the expected salsa with this parameterized approach. So if you remember what we learned in the expected salsa, so actually here expected salsa, we did not use the target policy, which is from pi. Instead, we use all the possible possible actions in the current state. We call it expected salsa, as is shown here. Especially we need to sum all the possible actions for this Q value. Then similarly, we have two cases. The first one is episodic and discounted. The second one is continuing and undiscounted. So the two cases. The second case is about the TD error is different, right? The update is different because we're gonna use the average reward instead of the current, the estimated set value. So we're gonna use the difference between the current reward and the average reward. We call it differential return. Okay. So similarly to this semi-gradient expected salsa without RS. Then lastly, we learned this multi-step semi-gradient control method. So it's just kind of a extended version of the previous what we learned in the n-step control method based on the in the tabular cases, right? So this is for the off-policy prediction and control with approximation. Actually, we put a lot of time and efforts on this eligibility traces. So this is our focus in the last lecture. Okay, ET with TD error provides an efficient and incremental way of shifting and choosing between MC and TD method. Okay, especially in this ET mechanism, we have two parameters. One is trace decay parameter lambda and ET vector ZT. Okay, so this trace decay parameter lambda is to rescale or fading away ratio for the ZT. So in ZT, it's just nothing else. It's just like a rescaled or re-ratioed the gradient of the history data, history state value. So based on this this decay parameter, we first designed the first algorithm based on this lambda-based return. We call it offline lambda return algorithm. So what we learned is that we design, previously we used just GT with some step n. Now we kind of add this coefficient, that all these coefficients will gradually fade away this return. So it means that all the history of this one particular episode will be rescaled and has some contribution to the current updates. After that, then we combine this lambda with the ET. We designed this the new term, the new update vector. We call ET vector. How we update it? We use the gamma and the lambda together. Okay. Then we use actually both the coefficients are in the range between 0 and 1. So actually, if you time them together, it becomes very small, but it's a kind of rescale vector. Okay. Then plus the gradient, okay, lambda with this estimated state value. So it's nothing else, just like positive or negative contribution to the estimate. So we put this one, and we can switch the previously what we designed the approach that focus on the forward view. Now we switch back to the backward view. Now we don't need to maintain multiple steps data. Now we just need to stand at the current state and look back what we cover, what we walk through. Then we just get all those data and update my current state. So in this sense, we designed the TD lambda algorithm. Okay. To improve TD lambda, actually we learned that there's some issue with TD lambda, because it is we cannot real time update it. We need to wait until the end of episode. So now we designed the n-step truncated TD lambda and the online lambda return algorithm. So the online lambda return algorithm is the improved version of n-step truncated lambda. Okay, so yeah, if you look at the detail, you will see what's the difference. Why we have those n-step truncated and online lambda return algorithm. Okay. Especially for this online lambda return algorithm, if you remember, so it introduced a heavy computation cost compared to the n-step truncated TD lambda or the TD lambda algorithm, because we want to make it online. I mean, when we make it online, it means that it needs to every intermediate step, it needs to update the weight vector from the beginning. So which introduce a lot of heavy computation cost. But yeah, it's online, so you can update the state faster. Okay. So for the linear function case, if this online lambda return algorithm, then we consider the linear case. Actually, we have a true online TD lambda algorithm. So it was published in 7 years ago. So a team they found the very concise form to do this true online TD lambda. We don't need to go through from the beginning every step. We don't need to go from the beginning, we just need to calculate some linear product. Then we can update the value. Eventually, we learn the salsa lambda for control. Okay, salsa lambda is just, if you remember, we just introduced the the from TD0, TD is for the state estimation. Salsa is for control, means that we're gonna update the Q value, the action value function, which means that if you every time when you look at salsa as a state action with a reward and another state action, so you always need to have the state action, reward, state action, a pair. Okay, then with this the pair, then we can update the previous the action value. So similarly, we use the lambda to rescale those the so from switch from the forward view to the backward view and update the vector based on the dt. So it's kind of we introduce this gradient. The is a positive or negative gradient to contribute to the current state. Okay, this is what we learned in the last lecture, especially these ET traces, agility traces, ET mechanism. So this mechanism actually improves the performance and efficiency a lot, and it has been studied a lot in the past 20 or 30 years. A lot of approaches have been proposed based on this mechanism. So yeah, okay. So you can open your iCampus, or I will open the link for you. So I will turn on this is the QR code. So if you don't use, you didn't bring your laptop, then you can use your smartphone. So you can be, so it's like 12:13. So we will finish this, we have 10 minutes to finish the quiz. So we will finish quiz in the 12:23, okay? So you can open it and refresh. Then it's open. Can you see the link? No? In the iCampus, there's a link. Can you find it? In the week 13, there is a quiz assignment. Inside there is a quiz link. And click, you should jump to the quiz. Okay. Cannot? Okay. Okay. Okay, wait. Let me reset the time. Actually, I don't know the what is the internal process of this setting time. Okay, I set the time 12:20, so I guess there's a okay. So how about now? Please check your iCampus, or you can scan. Available? Okay. So we'll finish this quiz until 12:25. 10 minutes. internal check slot. Three minutes. 1 minute. Okay, you should submit. Okay. It is. Should be maintained. Yes. It is. Yeah, should be maintained. So one of the option is should be maintained. I guess I delete some. Okay, please submit. So I'm gonna close if you haven't submit. The last one, okay. So okay. So today I'm not gonna show you the statistics, okay? Yeah. So we will just briefly go through what we learned. Let me stop the. So now we are going to move a very important topic, which is policy gradient method. Okay. In short, PG method. PG method serves very important aspect in the reinforcement learning. Most recent research results are based on this policy gradient or related, they could be kind of extended. Okay, if you carefully learn this topic, then after this lecture, you will be able to read those recent research paper related to this topic, like the PPO, the proximal policy optimization method used in the ChatGPT, or there could be other approaches like A3 C, A3C. So it was asynchronous advantage actor critic method. Okay. So yeah. So before jumping into this policy gradient, we just first look at this what I showed you in the week 2, the slide week 2. So at the time I mentioned that there are two major approaches, policy-based method and value-based method. Actually, before this lecture, before today's topic, all the methods we have learned those are value-based methods. You remember, we always check the state value functions, action value functions, and we also introduce the parameterized those two functions. And on top of that, we introduce the ET mechanism, the lambda and the z, to improve the efficiency. So at the time, there's also I introduced like very short introduction for this policy-based methods. Now I showed you what is the policy, and actually until today we're gonna learn this policy-based method. So at the time I showed you what is the policy. Policy is like a brain, like a strategy, or like the way to choose the best actions in some particular states, right? We find this optimal apply through training. So there are two ways, the direct way and indirect way. Directly means that we can directly update the policy. Okay, indirect way is that we're gonna update the value function, the state values, and based on state values, then we update the policy. So actually, in the past many weeks, those approaches we have been learning is the indirect approaches, indirect methods. Okay. Now in this lecture, we're gonna jump into this direct way, which is policy-based methods. Also, in the week 2, I showed you what is a policy-based method. Actually, after the lecture, many students came to me and asked, what is this meaning? What's the difference between value-based method and policy-based method? So if you remember another figure, so value-based method is just we put a lot of different values, and based on value, we make the decision. The policy is that we just directly put the policy here, and we follow the policy, we update the policy. So at the time, since there's no background, I cannot explain too much. There's no proper basic knowledge of all those background. So I just briefly, very simple, give the very simple explanation. Okay, so so this is a policy. What is a policy? Policy is kind of define a mapping from the state to the corresponding best action, and it also can be the probability distribution. That's why we have these two definition of policy. Two types of policy. It is a deterministic or stochastic. So mostly we are dealing with the stochastic policy. Okay, so this is what we learned at the beginning of this lecture. Now today we're gonna jump into these policy-based approaches. So as usual, let's look at our IR framework. As I mentioned, so actually since the beginning of this course, we kind of gradually developed multiple approaches, many algorithms from policy, state value function, action value function, parameterized with W vector, the weight vector, and introducing the eligibility traces, lambda and Z vector. And there's some iterative process. If we want to update the state value, then we can update the policy type. We can also update the action value, then we can update policy type. We design all those algorithms. So today we're gonna work on this policy type. Okay, previously we only have you give what is the policy? Policy is we give a state, then it will give you an action. So it's a policy, right? Today we're gonna use the new parameter, which is theta, to parameterize policy. So we should directly learn the policy based on the state and action, based on the environments. So also we are shifting our objective. Previously, if we state value-based approaches, methods, our objective is to maximize the expected return, which is a cumulative reward. Now we are shifting to the objective, which is maximize the performance of the policy. So the thing is how we can define the performance of the policy. Okay. So yeah, the important part is that today we're going to introduce a new parameter for the policy type. So as I mentioned, so in the past several weeks, we have learned a lot of this action value based approach like semi-gradient SASA. So they all choose action based on the values, action values or state values. So in this lecture, we're gonna learn this policy gradient method. So it's another type of method of reinforcement learning. In short, we call it PG method. It is a parameterized policy without value function. So there's no value function anymore. We just directly work on the policy. But we can still sometimes we can use value function. And so for helping the policy update, for helping policy gradients, but it is not required. So we can just we can introduce the value function together with the policy gradient. So we introduce this new notation theta. Okay, theta belongs to the real number with d prime dimension. Okay, real number, and follows for the policy parameter vector. So as I mentioned, now we are moving from the previous setting policy. It's like deterministic, or let's say target policy, to the parameterized policy. We use theta to parameterize phi. Since we're gonna learn it, so which means that we're gonna find some parameter. So this is a vector. This will be a list of vector. So this vector will update the policy. Will change the policy's, the direction or some combination. So the definition of this part is similar. The important part is that we introduce the theta. So policy gradient and actor critic method. So before jumping into all those details, we first give the overall what are we gonna learn. The first one is the policy gradient. Another one is actor critic methods. Okay, so actor critic method is it's like the method we learned. If we introduce value function together with policy gradient, then it becomes an actor critic method. So firstly, as I mentioned, our goal is to design a performance. So the object in the previous year, to maximize the performance of the policy. How to maximize the performance of policy? We need to define the performance measure. How to measure whether the performance is good or not. This is the first objective. What we do is that we define this scalar performance measure with j theta. You can consider it as an objective function. We're gonna optimize it, okay, to approximate, to minimize the error. So we try to maximize the performance. So previously we tried to minimize the error. Now in this scenario, in this sense, we're gonna maximize the performance, which means we're gonna do the gradient ascent in J. Okay. With this setting, we design our general update process, which is in this shape, theta plus 1. So you remember the theta plus 1 is the policy parameter. Okay, it will like decide the policy, the probability of the policy. So we just step by step update this theta. Theta t plus alpha. Alpha is, as in euro, is the step size. We do the gradient to this performance measure. Then this notation, the gradient j theta t, is a stochastic estimate. Okay, so all the methods follow this general update process called policy gradient method. Okay, PG method. If we use both policy and value function, then those methods called actor critic method. Okay, actor, here the actor is a learned policy, critic is the learned value function, mostly state value function. So we're gonna look at this AC method later. So as you may sometimes you may find this term in different areas, AC, actor critic method. Now you know what is this meaning. Actor, if you just look at the name here, actor and critic. Actor is the agent or the entity that decide the action. Then critic is like the guidance to tell you whether your action is good or bad. It's like you have an actor to do the action, then you have a critic, you have a judgment, you have a judge to decide whether your action is good or bad. So if it's a bad action, then I give you some, oh, this is bad action based on my state value, okay, value function. You may don't do that again. Okay, so now we come to this policy of approximation. So we first define the parameterized numerical preferences. We use H for each state action pair. So here we introduce this new, we call it the numerical preferences. Okay, H as a theta. For each state action. So you can consider is that. So it's like for a particular state and action, then with a parameterized, then the probability of this action. So we use the exponential softmax distribution to define the policy pi based on these preferences. Okay. So the action, then when we define this H, the preferences, the actions with the highest preferences means that it will have high probability being selected. Especially we define here, we define this pi equals the softmax distribution. So if you learn the deep learning or other machine learning, you probably are familiar with this softmax distribution. So basically it just kind of map the variable, the input. H is the input here. Okay, it's a state action value parameterized preference. Okay, it's like input. You can consider x in x. So you just generate the like probability from 0 to 1. So if you have a higher value, h is high, then it will close to 1. If h is more, then it will close to 0. So you kind of rescale your action value. So in this sense, actually, we define this pi in this way. So the denominator should be sum to 1, right? So I mean, it's just kind of sum all the possible state action pairs. Okay. Here the h can be parameterized in any form. Okay. So actually h is, you can consider it as the feature vector, feature construction, what we learned in the tabular case, or in the parameterized those approaches. Okay, in the action value function or state value function, we can use the neural networks. So the theta will be inside the h here. The theta in the h will be the connection weight. So if you design a neural networks, so the theta will be the connection weight. You need to update based on the neural networks this algorithm. It can also be linear in feature vector. So the XSA, so actually this XSA is just kind of lead to the HSA theta. So HSA theta you can just consider as a feature vector. So if it's a linear function, we can just directly define it with the theta transpose theta times dot product with this feature vector. Okay, if it's a linear case, so this is a linear combination, right? So if this is a linear combination, this x can be constructed by any those feature construction approaches, namely like polynomial, Fourier, and higher coding. Yeah, different kind of those approaches would we learned right before. So, but mostly in recent years, mostly we just use neural networks because it has a higher, better approximation, more flexible approximation performance. Okay, that's why it's kind of introduced deep learning with reinforcement, like deep reinforcement. So we look at some advantages for this kind of setting. First, we can approximate policy based on the softmax, and that will lead to approach a deterministic policy. So previously, when we designed different approaches, we use the epsilon greedy action selection method. Like we do the greedy action selection. Sometimes we also select non-greedy actions. So which is kind of random, right? Random probability. So it means that actually it's kind of reduce the learning rate and bring some higher variance. But if we directly approximate policy based on the softmax, actually we can approach deterministic, means that the optimal policy, it can reach the optimal policy instead of hanging around, moving around to check different to explore the environment. So actually this approximation policy can have those exploration. The second advantage is we can select action with arbitrary probabilities. Okay. The third one is making the problem become simpler in some cases, because if you remember, so some of you may question that there will be very limited use for the action value function or state value function, because those functions, you need to define very carefully for the states and actions, right? Define very carefully and state those actions and the state value, and then you need to update. So sometimes when you design them, the design the way design approaches may affect the final performance. Sometimes, many times, it may just may not work well. So, but for working on the policy directly, actually the problem becomes simpler. The last one is the choice of policy parameterization opens the door for prior knowledge of the desired policy form. So previously, you need to work on the action value and state value functions, right? So for all those, for those kind of shape, you need to put your kind of transfer your domain knowledge to this action or state value function, the format, the framework. But sometimes it's just difficult to put those domain knowledge to a particular, to the action value function or state value function. But if you work directly on this policy optimization approximation, then you don't need to care about the transfer the domain knowledge to the action value. You can just directly put your domain knowledge with the policy parameterization together. So actually, this is the most important reason, and it also kind of broadened the use, the application of this reinforcement learning. Okay, before jumping into the detail of some approaches, methods in the this PG methods, we first look at some simple example, which is we call short corridor with switched action. So the setting here is that we have a reward. So always we need to have different settings. Reward per step. So whenever you move, you have a -1. Then action, you have either left or right action. Then a special case is that when you reach to the second, let's say the second stair, it will reverse your action. If you move the left, it will reverse to the right. If you move to the right, it will reverse to the left. So this is a special setting in this case. So we also simply define this feature vector, x as right, x as left. So this s, we don't differentiate s. So s can be any state. Then we just define the action, right or left. So as I mentioned, this is a feature vector. If you remember here, the feature vector, which is related to the h. So it means that actually the h here will be this feature vector we define here. Okay. If we use the approach what we learned before, like epsilon greedy action value function method. So if you remember those approach epsilon greedy action value function, we need to do we choose the action, the greedy action based on some probability, and choose the non-greedy action based on the probability, another probability. So actually which is defined in this way. So for example, we can choose right action with probability 1 minus epsilon divided by 2, because we have only 2 actions. So epsilon will be divided by 2, or vice versa. So means that if you choose the right action, then the left action will be the epsilon divided by 2. Okay. Then if we give a specific epsilon, which is 0.1. The method we learned previously can only achieve the value, the action value less than either the left or right is that -44 or -82. So if you look at here, this is so epsilon greedy left, the x-axis is the probability of a right action. Then the y-axis is the state value, the performance mirror. Okay, it's like in each episode. So means that how many steps, right? It's kind of a mirror. How many steps we can reach to get the best performance. So if we run this, then epsilon greedy left or epsilon greedy right, it can only achieve somewhere here, like -82 and -44, about here. So it cannot reach better. But actually, if we look at all the performance, the probability, if you vary the probability of the right action, actually the optimal policy should be somewhere here, close to this minus 11.6. Okay, this is optimal stochastic policy. If we just run the epsilon greedy algorithm, the action state value, so actually it's hard to reach this optimal policy. We may get closer, but still far. Okay. And also the optimal, if you look at here, the optimal, this right action probability is 0.59 around here, about this location. Okay. Then if we have the policy approximation approach, a PG, policy gradient approach, actually we can reach this optimal stochastic policy. Okay. So when we say optimal, means that this policy shows the best, our target policy. When we say the stochastic policy, means that the action, the selecting action is based on the probability. Okay. So as I mentioned, if we use the policy gradient method, it can do much better, as it shows here. It can learn the optimal policy. The right action will kind of approximated to the 0.59, achieving the minus 11.6 value, which is a very big leap, the improvement compared to the action value approaches. So this is kind of a direct experience between the action value function, what we learned before, and the policy gradient approach. So now we jump into the policy gradient approaches. The first one we need to take a look at is that policy gradient theorem. Actually, this theorem is very important. It serves the foundation of all the policy gradient approach. So it's a theoretical advantage. This action probability can change smoothly as an action of the learned parameter. So previously, usually if you run the action value function based approaches, so every time you need to actually change the action kind of very not that smoothly. You may sometimes you turn left, suddenly jump to the right. Instead of changing the probability, okay, the left probability will be reduced gradually, and the right probability action will be increased gradually. So in this case, actually the running process will be more smooth. Then so now we are considering the episodic case. Firstly, yeah, we define the performance measure, which is the objective function, as the value of the start state. Okay. So this is setting. We define what is the objective function here for the episode. So which is defined in this way. J theta is defined as the V pi theta as 0. So means that every episode starts from this state. Okay. So we may generate many episodes. So every episode will start from this S0. So now our performance measure objective function is this. We define in this way. The V pi theta is 0. We just want to optimize this state value function based on this S0. Also, for simplicity, we don't consider the discounting rate, okay, which means that gamma equals 1. But actually later when we design the algorithm, this gamma can be between 0 to 1. So now we have this policy gradient theorem. So actually this is there's a long proof process for this theorem. So based on this setting, and we can derive this kind of proportional relationship between our gradient, the gradient of the objective function to the gradient of policy. Actually, our target is to build the link, the relationship between the our objective function to the policy pi. So this theorem exactly give this shape. So it tells us that here the mu s is the state distribution on the policy pi. So actually it gives the how frequent of the each states we visit. Okay, and q pi sa is the action value, right? Action value function, action value. So but we use a, so it actually is just sum all the action value. Then we do the gradient to the policy based to respect to the theta. So now actually this is the PG theorem. We look at this, the proof of this gradient. So actually there's a 2-page proof for this gradient. And this gradient PG theorem is very important because it just serves the foundation of all the PG approaches. With this theorem, then we can develop different algorithms. We can introduce different parameters inside of the algorithm. Okay, so you need to carefully understand what is the meaning here, each component. Okay, and we also, let's do the deriving process for this the theorem. So we start from this the gradient v pi s. Okay, because when we define the performance mirror, we use j theta. It defined as v pi theta as 0. Actually, we specified the performance mirror will be starting from S0, but in when we derive, we just put S0 as any state. Okay. So if we derive in this way, v pi s is just the state value function, right? Actually, it can be represented by its expectation of the policy and times the action value. Okay, so this is, you can check the Bayerman equation, the dynamic what we learned before. So you can extend v pi s to this the sum pi a under state s times the q pi sa. So it tells us that actually, if you directly look at here, the pi, what is pi? Pi is the probability of the action. This probability times the action value, the quality of an action from the current state. And we sum up them all, we can get the state value. And also look at here. Right hand side, I put this the tree backup diagram. So our goal is to find the gradient of this state value S, right? With this action. Okay, so now we can, with this is q pi sa times the policy sa. Then we can calculate different kind of v pi, the value. This is the Bayerman equation. The dynamics tells us, right? Now, since we have this gradient which is respect to the theta, actually we omitted the theta here. Actually, every of them has the theta. We omitted the theta for simplicity. So we need to do the gradient, and both pi and q pi is theta parameterized. Okay, if you do the gradient, partial gradient to the respect to theta, we need to do this calculus rule, right? We need to both sides, the first part and the second part, to the gradient, and we use the plus them, sum them. Then we move out this sum operation of all the actions. Then we can continue. So especially, so our target to find the relationship with this pi, the gradient of pi. So the gradient pi is already here. So actually we are going to work on the later part, which is the gradient of the action value function. So look at this q pi sa. As I mentioned here, the q pi sa can be calculated by all the surrounding next state, all the possible next states, right? So Q pi SA will be equals to reward times the V pi S prime. This is exactly what we do here. So this Q pi SA can be expanded into this way. The reward plus the neighbor or next state, the next possible states value, and times the transition probability. So there's dynamics, the environment dynamics from S to S1 prime, S to S2 prime. It also need to times the probability of the environment. The environment may decide what is odd that from the states S to the S1 prime. Okay. From Q pi to this, so we can expand this Q pi. Actually, this is what we learned in the Bellman equation, the DP, dynamic programming, or the MDP. So the dynamics what we learned. Now we're gonna continuously working on this this shape. So for here, if you just put, because we have this gradient, so this gradient will work on the theta. Actually, this is the constant number, and this V pi is parameter with the theta. So actually, if you times this part to the R and times this part to here, this the first part of this sum will be 0, because we do the gradient. Actually, it's nothing to do with the theta. Will become 0. Then put the second part to times this the V pi, so which will result here. Okay, so since the yeah, so you will see the transform, right? So this part will be disappeared because we do the gradient. This part will be 0. Then we move this gradient to here, which is the gradient of V pi S prime. And the dynamics also changed because the rewards already been decided. Okay. So if you now we look at this from the beginning, look at here. From the beginning, the V pi S to this V pi S prime, actually we have this recursive shape. Then we can expand, rolling this V pi again based on the current shape, right? Then the V pi, the gradient V pi S prime will be expanded in this shape. Again, we can expand V pi S double prime again. So if we continuously doing this process, we will have, so we just move this the first part. So the first part will be kind of there will be multiple sum together. So we just move the first part, the gradient pi a under x q pi x a here. Okay. Then we put all those this pi, the probability, the policy times the dynamics to here. Actually, which is we can summarize it into this short form, which means that actually if you look at here, it's just the dynamic from state S with an action, it will jump to the S prime. Then we just sum all those possible S prime, right? So this is the dynamics. So then we just, there is a sum operation for all different kind of action. So then we just rewrite in the short term, like we just generate this probability. This will be from the current state to arbitrary state with some step. So this step will be infinite, because if you unrolling, so this shape, it will reach to the infinite, right? So we will have this probability from a particular state to arbitrary state with some step k. So this is the kind of summarize all those transition probability. As I put it here, this probability S to X K pi is the transition probability from state S to the state X in K step with pi. So it just summarize the transition probability from a particular state to any states. Okay. Also, I put the reference here, how we get from here to here. This is also from the Markov decision process of Beerman Markov property, the dynamics of the environment. You can do this way, derive. So obviously, if from here to here, you can switch, right? So now this is the first part. So until here, we already kind of developed some relationship between the policy gradient. Okay, this is policy gradient with the target objective function. If you remember, the J theta is defined in this shape. Now we just replace this S with S0 to see what will happen. So now we put this S0 here, and means that from S0 to any state, we can the probability, the transition probability, then times this pi S Q pi. Now we can just rewrite this part as a eta S. Okay, eta S. So I mean, we just simplify it as, because it's just like multiple step transition probability, right? So we just give the eta S. So we can do the kind of simple mathematic trick. We just put another term, which is S prime eta, sum the S prime for all of the eta, and divided by the here. So these two parts will be cancelled, right? So actually it equals the 1. It just equals the original, right? These two parts will be cancelled. Then in this case, what is this? So if we look at this eta S divided by the sum of eta S prime, so S and S prime, actually they share the same set, the state set, right? The whole state space. So it's just like we can just say that it covers all the transition probability of the states, the sum of all of them. Then we put the particular state transition probability, the ratio. Actually, it's just the frequency or the distribution, state distribution of these particular states. Okay. Then we can just write the mu S here. Now, actually, we already have the shape now, which this means that it's actually proportional to, we can just consider the first part as the coefficient, some number there, because it's based on the dynamics of the environment, right? So it's proportional to this shape, right? So now this policy gradient theorem has been proved. Okay. So yeah, try to understand this policy gradient theorem. So this is a very important concept in reinforcement learning. And if you, so I mean, most of those recent years research result, they develop their algorithms actually based on this theorem. Okay, you need to have the first have this theorem, then you can have all those different kind of approaches. Okay, so yeah, let's take 15 minutes break and come back. So based on the policy gradient theorem, we can design different kind of approaches to algorithm actually. So the first one we're gonna take a look at is the Monte Carlo policy gradient algorithm. Okay. So how we derive this algorithm? First, we define. So we based on this theorem. Okay, based on this theorem. So we look at here. Okay, the mu S is the state distribution probability of the states. So just sum all the probability of the state. Then the Q pi SA gradient pi. So these two parts actually, if you look at this shape, if you then link to the expectation of the random variable, look at here, okay? Actually, the state S, we can put it as a random variable, and the mu S become a probability, right? The mu S itself is like a probability of the state. Then you can just rewrite it into a expectation shape. Remove this sum S, mu S, because this mu S you can consider as a pi here, probability. Okay, times then xi is the remaining stuff here. Then the difference is that now instead of a sum, iterate or going through all the states, we just put the state as the random variable st from small s to the capital S, become st. Now we just transform our target, the gradient of the target objective function to the some expectation of the based on the policy pi. This expectation. Actually, with this expectation, we can already derive the first update process. We just put this expectation, this gradient j theta to here. So the theta t can be updated in this way. Then we just put the remaining part to here. So sum all the possible actions for this action value times the gradient of policy. Okay. So I mean, this is valid update, but the thing is that when we look at this the shape, it actually you need to sum all the actions. Most of the time when we deal with the real world problem, the action space is huge. So we want to do better. Also, this Q hat here is the approximation to the Q pi, is the target action value. Okay. So can we do better? Actually, we can do further extension if we look at the shape here. Okay. Then which leads to our first algorithm called reinforce. The reinforce method, which was published in 1992, and this method further extended the previous updates so as you can see here. So somehow this group of person find this. Okay, actually there is a Q pi STA here. But usually before the Q pi, we usually put the policy. Policy times the action value function, then will lead to the state value, right? Action value to the next state. So then we just put this this division, the fraction here, into this expectation. Then we put the pi AST here, another pi ST here. Okay, so that it doesn't change the value of this expectation, right? Because yeah, the cancel just equals 1. Now, what we look at here is that we use the expectation definition again, as I put here, the expectation of the random variable xipi. Then look at this shape. So this shape, this is the probability of the sum all the possible actions based on the policy pi, which is parameterized by the theta. Actually, this is the expectation, another expectation of the based on the policy pi. Okay. Now we can just, because we already have an expectation, the two expectation, we can just use the one is enough. Then we can just cancel this part, merge it into the expectation based on the pi. Then put also based on this so you see the pi itself is a probability, then the later part become the random variable, all the action A then transfer to the random variable instead of enumerate all the action. So we just put the AT. Okay, wait. Okay. So this small a become capital AT, become a random variable. Now actually we can rewrite this shape into this way. Actually this shape is very concise. And if you look at this Q pi STAT, what is this? It's just the return. Okay. If we consider the Monte Carlo method, the Q pi is just the return, the reward, accumulated reward, right? So step by step. And we put to here. Now the shape become very concise, very simple. And with this shape, we can rewrite the update. Previous update was in this shape. Now we just use this part, GT gradient pi divided by pi to do the update. Okay. Now this update process will be like this: theta plus 1 equals theta t plus alpha times GT times this division. Okay. Actually, we can do further kind of simplification. If you look at here, the nature log x, the ln x, the gradient of ln x is equals to the gradient x divided by x. If you look at the shape here, the pi, gradient pi here is just exactly the gradient ln x. Then we can further simplify it into this shape. GT ln pi AT ST theta t. Okay, so actually this is a very if you look at this derivation process, and if you look at those modern recent years published papers, most of the time you will find there's a log there. Okay, log, but they just put log. If you put e as the base, then it will become ln. So this is where those log come from. Okay. So, but if you don't know this background, you just look at those approaches, you find the gradient based on the log and with some action and states. It's kind of confusing why there's a log there. Okay. If you know this background, you will know how those log operations come from. So now we have this very concise update process. The theta, we can update based on this GT. So here, if the GT is a Monte Carlo return, right? Now we can design our first algorithm, which is reinforce. We call it, the name is reinforce because the first person, people who find it and named it, and which is the Monte Carlo policy gradient control. So since here we are always updating the policy, so naturally it would be a control problem. Okay, we are control the policy. So with the new update the form, then we have this approach. Let's take a carefully look at this reinforce algorithm. So this is the episodic form. Similarly, so there's input is a differentiable policy parameterization. So the policy pi is parameterized by theta. So this is the input. So initially, actually, our input will just be like the theta, the vector of the theta. So then the algorithm parameter, the step size, as usual, the policy parameter theta belongs to, initially we just initialize the x into the 0. So actually the pi depends on the definition. Okay, actually in our case we define as the softmax, right? If you remember, at the beginning we defined as pi as a softmax. It would generate the 0 to 1 probability based on different kind of feature vector. Now we loop forever for each episode. We generate an episode based on the problem setting from the beginning, S0, action 0, R1, until the terminal state, following the current pi. Okay. So we just loop for each step, episode t equals 0 until the step before the terminal state. Now we just update. We first calculate the return GT. Return is when we derive the policy gradient method, we mentioned that there's no discount. Actually, here for this generosity, in general we just put gamma here for the discount rate. So actually, there's a further discussion about this gamma in this algorithm. Initially, there's no gamma, but later on they put it here. Actually, gamma has some purpose here. But we will, in this lecture, we will not look at the purpose of gamma. So you see here, this is simple, right? It's just how we calculate the return from the for the particular episode from the 0 until t minus 1. So if you look at this index, the iteration, k equals t plus 1. Initially t equals 0, that means the k equals 1 to t. So k equals 1 to t. So it's like it just iterate. So t itself is also t is 0, then just equals the 1 minus 1. So the first item I'm saying, right? The first one, 1 minus 1 is 0. Then we will be just equals the AK 0. The R 0 here. R 0 will be the actually it should be R1, right? So because we are starting from the t equals 0, it will be R1. Yeah. So k equals t plus 1, t is 0, actually k equals 1. The 1 minus 1, so the gamma with to the power 0 and R1. So which is the first reward here. Then we just accumulate this process to G. So the G will be the return. That is actually just the Monte Carlo return. Then put here G and do the gradient to the lamp pi. So we call this lamp pi as the eligibility vector. So actually this name, the naming here, so don't get confused with the eligibility trace vector Z, right? So it's different. Like in those academia research papers, different people give different names. But in our textbook, we just use this eligibility vector. Yeah. So this part is just what we derived before, right? To the policy gradient divided by the policy itself. So also when you look at the move back to this, we need to help specifically look at this. What's the meaning here? So we do the gradient to the pi divided by the pi. The pi is the probability of different action. We do the gradient is the different actions changing rate, right? Different action changing rate and divided by that action probability. Actually, it just gives the ratio how much the particular action will be like readjusted, rescaled, the probability of it, right? So if you run some like greedy what you will probably see some if you use the length of the size of the error, so you will probably see the size of the error can correspond to the probability of an action. So you probably see the shrinking of the size of the error and some enlarging size of the error corresponding to the probability of the particular action. Okay. So this is the meaning here. So if we use this, one more step. So at the beginning, I mentioned that if this pi is parameterized by the softmax, right? Softmax function. Then inside of softmax, the variable, the input is the preference, right? Preference, the action preferences, which is the H. We use H, S, A, and the theta T, theta. The theta is located there. So H can be the different kind of settings, can be done by the neural network, can also be the linear function. So if the H inside of this pi, which is the softmax function, inside of this pi is the linear function, what we can got this result. We have this very concise result. So based on the setting of softmax in action preference, which is here, the pi, we design the pi here, right? The softmax, and H is a preference. if H is defined by the linear function theta transpose T, the theta transpose times X, the feature vector, we have, if we do the derivation, then we have this. If you do the gradient ln pi, you will have this shape. X as a minus sum all the action to the pi, and times the feature vector of the particular action. Okay, so the derivation is located here. How you can derive this result? Actually, it's, if you look at the textbook, it's one of the exercise in the textbook. It asks you to derive this process. So from this, so let's look at here how we derive this process. Because this linear case actually is quite important. Even for the neural networks, inside of before the activation function, they are the linear combination. Okay, if you have this shape and put it into the activation function, then you have a very easy, straightforward calculation process. Okay, so from the beginning, we do the gradient to the ln pi. So you look at the pi. What is pi? Pi is the softmax. Softmax is the division from the e to the power h, and sum e to the power h. So this is the division. So if you put a ln here, it will just become the nominator minus denominator, right? Which is exactly here. Okay, we just divide it into two parts. Nominator, denominator. Okay. So ln EH as a theta minus ln sum operation. This is the first operation. If you look at here, then if you put this okay, you see the ln with the e. Actually, these two will be cancelled. Then it will just equals to h. Okay, the h. What is the h? H is just, if you do the gradient to the h, it will just equals to the feature vector. So the first part is done. You already have it here. Okay, h is the linear function right here is defined in this way. If you do the gradient with respect to the theta, which just equals to the feature vector itself. And deal with the second part. The second part is the ln sum operation of this exponential function. So what we do is that we use it again. Okay, from here we do the so actually you just extend this ln, okay, into this shape. So you know the how did I divide this? Anyone? So actually the log, the ln here, we remove. How did I derive this? So EH divided by EH. Since we have this division, then okay. So we reverse use the previous one. Okay, I almost forgot this. We use this operation here. This operation. Okay, this operation. This gradient ln x equals gradient x divided by x. Reverse uses. Okay, so from here to here, then we can derive to this shape, right? So this ln, the sum operation will be expanded into this way. If you look at the previous operation. So now we just put the linear function of this h to here. We put the theta tx here, okay? The transpose theta and transpose theta xx. Now we do the gradient. So since we can move out because this is a sum operation, so there'll be multiple e sum together. So the gradient will do to each component. We can simply move out the sum operation out to here and put the gradient inside. Then we do the gradient for each component. Okay. So for the gradient, we need to do the gradient to the theta. So the e, the gradient to the derivative to the e will be just equal to e itself and times the chain rule, right? The theta x sp. So since this is a linear combination, then you do the partial derivative, it just equals to the feature vector itself. Okay. Then the bottom side is the same. Now we just rearrange the order, move out the x to this fraction out here. Then what we see here is that then we look at here. This is another pi, right? This is another softmax definition. Then b pi b as theta. Another softmax. So we just write pi b. So now the shape is proved. So in this shape, we can easily to calculate this gradient with the feature vector and the sum of all the possible the actions for a particular state. Okay. This is now we will look at the example how we can use it in the algorithm in here. Okay. Means that now this lambda pi will be equals to this shape, this difference between the feature minus the particular feature of the state. So yeah, let's look at this example again. So in the previous example, we have this short corridor grid work, right? So the setting are the same, and the feature vector for all s, x. So we already defined this the feature vector. So the s is for all the states that we doesn't differentiate the states. Then right, left, and 1, 0, 0, 1. Okay. So the initial the theta will be 0, 0 initially. Then alpha we just define is 2 to the power minus 13. Then update process on the right hand side. So we use this MCPG algorithm. Then we also, because since this is the linear case, we expand this gradient length pi to this shape. Okay. Then since x feature vector for all s has two parts, actually we can combine them into one the matrix x, the feature matrix x. Okay. So now we generate an episode. For example, we just name the episode S1, S2, S3. Then the starting state is S1. So we can just generate the trajectory. Once it reaches to the goal, this trajectory is ended, the terminal state, right? So for example, here as an example, we generate an episode S1, S2, S3, S2 until G. So we also have this return GT. GT is calculated based on the here, right? But the difference is that here the GT for each step, the GT will be a little kind of a different value. But in our case, I just put the same value, minus 10, because we have 10 steps. We just consider all the return equals minus 10. Now we can use this update. So our algorithm, the MCPG algorithm or reinforced algorithm, is based on this update. Our goal is to update the theta vector, the policy vector, right? What we do is that also you remember what is pi? Pi is the softmax. Then the input is a linear function, transpose the theta times feature vector x. So with all those information, so you can do. So let me just use some. So we have this episode here, right? We have this 10 episode. Then each step we have the return. We already calculated the return minus 10. Then for the first step, this is the first step. T equals 1. The initial theta equals 0. So actually all the 0. Plus, so we just use this update process alpha, put here, times, then gt equals minus 10 times. Then the important part is that how we calculate this NumPy. With this NumPy, we just directly use the linear, the expanded version of here, okay, which will be equals to, so x as a. So you remember, so you need to see the action here. From s1 to x2 is to the right, which is corresponding to this feature vector with 1, 0. That's why we put 1, 0 here, because this is the right action. Okay. So this is first the feature vector. Minus, so minus here is actually the softmax operation, and with the x. So I just put the softmax the calculation as a function. So if I put the source code here, some implementation of softmax. So you give the theta, you give the x. The theta initially is 0, and x is the matrix, the feature matrix. Then put here, we first do the dot product, which get the h, which is the linear, which is it just calculate h, which is located here, right? Then put the h to the exponential function. Then we do the normalize h minus np point max h. Normalize it with the, then do the softmax operation. It will generate a probability from 0 to 1. This is what we do here. Now, after this operation, you will have, initially you will have this generate 0.5, then 0.5, this vector, okay? Now, then times this x, the x st. So remember here, so we have this summation operation, okay? This b is action. It will cover all the action. So this x here will be all the possible action from the feature vector, okay? That's why we put the x, the feature matrix here. It covers all the actions. So which means that this x will be equals to, this x will be equals to, so I just rewrite this one, right? So in Python case or NumPy case, you can just write down in this way. So now you do the dot product, you times you can just calculate, right? So which will be equals to 0.5, and the second one still the 0.5, right? So then all the remaining the option here is the 0.5, then the 0.5 based on the current setting. Now we just use since we didn't use the transpose, actually we put the t here, and 1, 0 transpose minus again, minus this calculated part, which will be equals to the 0.5 and minus 0.5 transpose. Okay. This is a calculated 0.5 minus 0.5. Now and then you can just others just straightforward. It times minus 10 and the alpha equals 2 to the power minus 13. Then theta just equals 0. eventually you can, so let's just calculate the value. It will be equals to something like, so theta is 0, actually you can ignore alpha. So it will be, so also minus 10 times 0.5 will be the minus 5, right? Will just be equals minus 5 alpha. This will be 5 alpha. Yeah. This is the first calculation, then theta 1. The first iteration, theta 1 will be equals to, right? This is how you can calculate. The next step, you just put the theta 1 to here, then there will be, we can calculate theta 2. Theta 2, theta 1 to here, and theta 2 with the updated theta. So this is just for one episode. So for each step, you need to update theta 1. So you can generate a lot of episodes, then calculate. Okay. So this is how you can use the previous algorithm, MCPG algorithm or reinforced algorithm. Any questions? Okay, good. So yeah, as I mentioned before, when you try to design or try to understand some algorithms, you need to be very specific to those data, those dimensions. So for example, what kind of dimension, what kind of data you need to be. Then when you write or update, when you have some idea, update some algorithm or try to derive your own algorithm, you have the sense that what kind of dimension of the data we need to deal with, what kind of the data structure is there. Okay. This is internal the calculation computing process. Okay. And clear this. So okay. So this is what we just did is this part, right? Then especially we need to calculate the lamp pi. We use the linear expansion of this lamp pi and do the update process continuously. Eventually, if you run it enough time. Now let's look at some performance for this. As I mentioned, how we calculate those update is theta, right? Now the episodes you see here, then with different alpha, different alpha. With different alpha with these hyperparameters, then you can adjust to check different performance. Here, the best performance for the alpha is the 2 to the power minus 13. Okay, the best performance. And the episodes, when it converges, it need to use about 700 to 800 episodes. Okay, so even though this problem is kind of simple, but it takes those kind of such large episodes to reach the converge or optimal state. The optimal state, as I mentioned in the beginning, which is a minus 11 points something, okay, close to somewhere here. This is the optimal state value and optimal policy. Also, if you this is the reward, total reward in each episode. Okay, so means that in each episode the total reward kind of updates up, increase, reduce for each episode, and it's the data here has been kind of averaged over 10 rounds, I guess, as I remember. Yeah. So still, when you look at this performance, you see here, what is the problem here? What is the problem here? As I mentioned, it takes a long time to converge, right? You see here, it needs to generate almost 800 episodes to converge to some optimal states. So assume that you train some model. Perhaps you don't have that patient. You just train to some particular point, then you just stop. Actually, you thought you already reached the best performance, actually you have it, right? And also finding this alpha is also takes some time. Then how to define this alpha? You can check what we learned in the previous some lecture. I showed you how we can define this alpha. It should be 1 divided by the uh, the average step size. Okay. So alpha we need to be kind of searched for. So if you look at here, the alpha, the subtle or delicate of this alpha, you see here there's 2 to the power minus 13 and 2 to the minus 14, 2 to the minus 12. So actually the minus 12 and minus 14, they have this 1 degree, 1 level difference that you have quite different performance. Okay. So this is reinforced on the short horizontal grid work. Now further, we can extend this reinforced algorithm, the MGPG approach or gradient, with the baseline. People find that actually we can generalize the PGT, policy gradient theorem, to include a comparison of action value to an arbitrary baseline. We use BS. So the reason we can put minus BS here is that if you expand this, so you just time here and times here, you will see here the BS when you expand this policy gradient theorem, the minus BS times this gradient pi, then you calculate it because BS itself does not relate to the action, does not relate to the theta. Then we can safely put the gradient to this pi. So, but see here, if you do the gradient to the pi theta, actually it just sums to the 1. Okay, it just equals to 1. Then because it just covers all the possibility, right? A. Then this will be equals to 1. Then you do the gradient to the 1 equals 0. 0 times any number will be 0, right? So that's why we can safely add this baseline in after this action value minus the BS. It doesn't change the relationship, doesn't affect the value. So the BS can be any function as long as it's not associated with action, because the action is related to the pi. The pi is we need to do the gradient. If you put it related to A action, means that it will be parameterized by the theta. Then when you do the gradient, so this condition does not hold anymore. Okay. In this case, with this new update of this policy gradient theorem, we can have a new reinforced, so-called reinforced with baseline algorithm. We just add GT minus BST. So usually we put BST as the value function, state value function, actually which will be linked to the actor critic method. Okay. So based on this setting, the overall the performance, the process is similar. So the only difference is we introduce the baseline. Here we use the baseline we use the state value function as the baseline. So this is the general practice. We use the state value function as the baseline. Actually, it also means that we are kind of linked between the policy gradient and value function, state value function. So because state value function involves the W, the weight vector. So in this case, we're gonna update both weight vector and the policy vector, policy gradient vector, theta. Okay, both W and theta need to be updated because this V hat is estimate of the optimal state values, right? So yeah, a little bit complicated. Also, this alpha we need to differentiate. The alpha is for the weight vector, or alpha is for the theta, for the policy gradient vector. So if you look at this performance comparison between this origin native reinforced and the reinforced with baseline, we see a clear improvement. Okay. So compared to the best performance in the previous setting, alpha equals 2 to the power minus 13, then the reinforced with baseline improved the performance a lot. Actually, within 100 episodes, it already reached to the optimal state. Okay, the optimal policy. Then with this alpha, different alpha, theta, alpha, and this learning rates for theta and the W vector. So actually, the reinforced with baseline largely very significantly improve the performance, right? We converge to the optimal state much faster. Now we look at another issue with this reinforced. So look at this reinforced update method. Just look at here we look at the GT, because since we are using the Monte Carlo method, right? The GT will be available at the end of the episode. But the thing is that even though this GT, the reward, is calculated, based on the real environment, real out the feedback from the environment, from this setting, any environment setting. But actually, this GT may introduce high variance in different episodes. Look at the example here. Assume that you have this game. This is a start state. With this start, so the game, you understand this game, right? So you have the opponent, you player and opponent. Then you need to just keep hit this ball instead of missing it. So we will just miss it, then you lose, right? Assume that this is starting state. Then from this starting state, the reward, the return, can vary very largely. Okay, very large. So sometimes if some good trajectory has a 100 return, some very bad trajectory has a minus 1,000 return. So which brings very high variance to this GT. So you put GT to here, so this update will be it will take a long time to converge. This is a problem, the issue in this reinforced algorithm. That's why we introduced this actor critic method. So previously we just used the actor, so that we updated the policy, right, based on those return and the policy, the gradient theorem. Now we introduce the critic. We just, we maintain the state values to check whether the policy, the action from the policy made is good or bad. So the critic just gives some suggestion. Oh, your action is really bad. Don't do that again, or try to reduce the probability of that action. Yeah, this is the role of the critic. So yeah, one of the way to reduce this variance is to use both policy-based methods and value-based methods, which called actor-critic methods, AC methods. Okay. If we replace with the GT with the one-step return, which is from the GT0, with this GT T plus 1, the GT, the one step, the difference, right? TD error. To here, the GT will become TD error. Then B is the state value. Then the TD0 will further be extended into this shape. The TD error, right? One step TD. Then the current step plus the discounted state value, estimated state value, then minus this V hat. Okay. Then times the later part. What do we learn? So now actually we introduced so we use the delta T to represent this part, okay? Delta t to represent this part. Then we just introduce the both policy gradient and the value, parameterize the value, and also let's say the parameterized gradient of state value, okay? So in this case, for this AC method, for this particular AC method, it's fully online and incremental. We can update step by step instead of waiting for the end of the episode to start update from the beginning to one step, then we update because it's the nature of TD0. Then we also introduced we had state values, right? Parameterize the state value. Then we will maintain the state value for each state. So each state will have a state value. Then with the state value, then we rescale this the gradient of policy. So we can understand this AC architecture from this diagram. You see from the left-hand side, diagram. If you look at here, so you have an environment. Now, if we don't have the value function, it's just purely policy gradient. Okay, we have an environment. Then the reward will be used by the policy. It can be the MC, the GT, right? The return directly to the policy. Then we just update based on policy gradient theorem. Now we introduce a value function. So this reward will go to the value function, then generate either if we use TD error, here the TD error will itself will update the value function, and TD error will also go to the policy, update the policy. Then actually in this case, the value function, so this TD error will actually affect the policy. Means that the TD error is adjusting to the error, not the directly reward through the policy, because the reward itself can have a very high variance. Then in this case, the agent will include both policy and value function. Then yeah, the framework kind of expanded, but just inside of the agent, these two parts are used together. As another diagram, if you do how you understand the AC method, so value function, policy purely policy based, purely value based, and mixed the method, actual AC methods. Okay. Any question? So based on this AC setting, we can design different algorithm now. So because we use the TD0, one-step TD, so naturally we can just have this one-step AC algorithm for the episodic problem. So the process is similar. The only difference is this delta, right? The delta will introduce the one-step TD error with this VPI with the baseline. And also we need to do both the weight vector and the theta gradient vector, policy gradient vector, and the state value vector together. So the alpha will be different. The two update process will have a different alpha, different step size. And this delta is this delta. So they use the same delta to update state. So this delta will be used to update the state value. This delta will be used for the theta, the policy gradient vector. Okay, the theta will be shared use. That's why in the previous we used the TD error, right? So now means that so usually, as I mentioned, for this process, this we had and the learn type, we can do the neural networks. Means that actually there will be two neural networks to update this W and theta. If we use the nonlinear functions. Now in this case is fully online, but one thing is that this is forward view, means that still we need to, since it's one step, we just need to wait one step until the next step, we can update previous step, right? One step. If multiple steps, we can still extend this algorithm to the multiple step passing algorithm, but still in the forward view. If we combine this one step AC with the eligibility traces, switch it from forward view to the backward view, then the process becomes much complicated. So you need to maintain 2Z. Okay, 1Z is for theta, the other one is for W. 2Z here. So each one will be responsible for rescaling or like adjusting the gradient. So for ZW, it's in charge of adjusting the state value gradient. For the theta, it's in charge of the gradient of the policy, right? So the ZW, Z theta, we need to maintain. Also, now that we use ZW, Z theta to the vectors, weight vector and the theta vector updates. So now in this case, actually, we switched from the forward view to backward view. Now we don't need to save, if it's multiple step, we don't need to save multiple step data there. Just based on the current step, we use the history data, the decay data, then update the current state. So especially here, we use, there's I here, is the one, okay? You just, what is that? Unit, the vector or matrix, okay? So this is AC with ET. So far we are dealing with episodic problem. So all those deviation and the settings are based on episodic problem settings. Means that there will be multiple episodes, the terminal state, then we can do it again and again. Then how about for the continuing problems? So if you remember how we designed how we derived the continuing problems, we defined the average rate, average reward. So here we just use the average rate, means that the difference between the current reward with the average reward. We call it average rate of reward per time step. So if you remember, you recall what we defined for this process. So actually it's the same to the previous one, what we derived. So this return, so there's unlimited action, so there's no end. Then we just divide the expectation and we sum all of them, divide, get the average, then H equals infinite because the time step is infinite, right? Then if you look at here, it just equals to the expectation of the inside. And we just put the T to the infinite. Eventually we can link it to this shape. So actually we look at this before. Also this mu s is the ergodicity assumption, ergodic, okay? So this mu s means that we can, from any state, we can visit all the states. So since the time limit is it's not defined, it's unlimited time step, means that through this unlimited time step, we can visit all the states. All the states shall be visited. And yeah, also another observation is that if you look at here, because since we have this mu s, so if you from any state, you can jump to another state. So this mu s prime, another state, actually can be represented by another state. They will have, because they have the same distribution, okay? So in this sense, actually the policy gradient theorem we developed in the episodic setting is still holds. Okay, we can, how you can prove, if you click, there's a proof I put in the appendix, you will see how we can derive this process. It's not that difficult. And yeah, the process is similar to the one we derived for the episodic case. So I put those each step, how they got you can check the detail each step. The basic setting from the beginning is the same. Each step how we rerun. So the one key difference is that previous just R, now it become R minus R theta, become the difference rate, right? Average rate. So yeah, others the condition what we used are the same, and yeah, eventually we got this shape from the beginning of this gradient V pi s. Okay, so now based on this derivation, we see that the policy gradient theorem works for both their episodic case and continuing case. Okay, so now we can safely extend the PGT, the algorithm based on PGT, to continuing case. So you remember the GT will be equals to the average reward rate. Okay, the difference, just get the reward difference, return difference. Then we just put the theta definition will be different. Previously the theta is just R. Now with theta R minus the average reward here. Okay. Then other part just similar to the previous one. So this is also the backward, right? Because we developed it based on the ET. So here I don't go to the detail how you can calculate those vectors, because if you look at the first example I showed you how to calculate, so the calculation process should not be difficult. Okay, and the most important part is just this gradient length pi. Now, how about the continuous actions? Continuous actions actually has a lot of application space, right? So, for example, autonomous vehicles, you want to train autonomous vehicles, those action space is continuous. So you can just use, as I mentioned before, so those rotating, acceleration, braking, all those actions are continuous. For those kind of space, if we use the episodic or discrete action spaces, that would be kind of a burden to define. We need to define a very big set, action space set, right? Actually, we can use some, since we are defining this pi, in the discrete case, we use the source of the max function to define the probability. So actually we can extend based on the normal distribution, which is use the normal distribution to define the policy pi. Okay, which is parameterized by the theta. So if you look at here, so this is a normal distribution, right? The Gaussian distribution. Then we can just easily to expand this policy pi parameterized by the theta, and we have the sigma and the mu. Okay, mu is decided will decide the mean, right? The sigma will decide the variance or deviation. So if you look at here, so different shape of this mu and the standard deviations combination. So the larger the sigma, then you have a higher the deviation. And also remember that the sigma should not be smaller than 0. Okay, always be larger than 0, but the mean can be negative. So these mu and the sigma are the two mapping functions. So from states to the real the d prime dimensional real number, okay, to the real number. It's like a mapping mu. Similarly, the sigma, okay. So since the parameter here, when we define the sigma, actually theta here, the theta has two parts. One is in the mu, the other one is in the sigma. Actually, it has two parts. So we can divide it into two parts to have this theta mu and theta sigma together. So the first part, just the mean mu, right, can be approximated by a linear function. The second one, so we use the linear function, which is defined here. Mu s sigma can be done by the linear function. The second part is the standard deviation. It shall be greater than 0. So we use the exponential function with the linear function. So e to the power a linear function. This is how we define. So this x mu and the x sigma are the state feature vector. Depends on how you define it. So yeah. So you can use those. For example, this x mu can be, the different kind of sensor data there, like sigma also. As long as you kind of construct the states. Yeah. So now, in this case, if we use the linear function as the mu as a linear function and sigma as sigma as an exponential function, we can directly derive the eligibility vector. And eligibility vector is the ln pi, right? The log pi function we design. So it's similar to the previous one. We extend the linear case of the EV, the eligibility vector of the MCPG algorithm. So similarly, for this pi definition, then each mu and sigma, if we do the gradient to the ln pi, gradient ln pi with sigma mu, sigma theta mu, theta sigma, then you can eventually have this shape, okay? So in this case, for the continuous action space, you can update the theta in this shape. It will be much easier for you to calculate from if you do the gradient from this original pi, right? So you have this shape. So we will not go to, so if you look at here, the mu and the sigma, mu is the linear combination. X mu is just the input feature vector. Sigma is the exponential function, squared exponential function. So it's not that difficult to calculate, okay? Yeah. Okay, so that's all for the policy gradient methods. So the contents in this lecture serve the foundation for all the policy gradient-based approaches. If you look at all different kind of approaches, most of recent approaches are based on this concept. Okay, and because it has a broader application area. Any questions? Okay. So now the summary. The summary is straightforward. So at the beginning, when we designed this policy gradient method, we designed the pi as the softmax policy function, right? Then our objective function designed by the v pi s0, the state value of the starting state, any episodic stuff from this state. With these two conditions, then we derived our policy gradient theorem. So we find that if we want to do the gradient theta, gradient objective function, actually this is proportional to the remaining shape. Actually, luckily, it links to the gradient of the policy. So our goal is to link the gradient of objective function to the gradient of policy. Right? This is the goal. Actually, we have this, the policy theorem proves that this is true. Now we have this general update process. With this general update process, we designed the two basic algorithms. reinforce without baseline, reinforce with the baseline. So we find some disadvantage in this reinforce without baseline, just purely based on the return, if it's a Monte Carlo method. Then we introduce the baseline. It doesn't change the theorem. It still works, but improve the efficiency a lot. Then still, so when we consider the reinforce with the baseline, still the GT has a high variance, right here. It still can, even though we introduce the baseline, kind of improve the performance. Still, the GT has a high variance, kind of reduce the convergence speed. Then we introduce the actual critic method. In this actual critic method, especially we look at the TD0, we introduced the both policy gradient and the state value gradient, right? Together, we need to update the state values function and the policy gradient together. Policy together. Then, does the policy gradient theorem work well in the continuing problem? Yes, actually we have those settings, and we prove that this PGT is still true. With this concept, then we can safely design different kind of algorithms based on the continuing problem setting, because the continuing problem setting will use the GT will be equals to the difference between the counter reward and the average reward. We call it the average rate of the reward or return. Then eventually we reach to this policy parameterization for continuous action. So for continuous actions, so we can use a continuous function to design the policy type. Then with this continuous function, with each the parameter in this continuous function, which is based on the normal distribution, they have either mu or sigma. They can be the linear function. Then we further develop those calculation terms. Then it will help to reduce the calculation burden in the algorithm. Okay. So yeah, this is all for today. And so this is the last piece of reinforcement learning course in this semester. Okay. And also it's very important topic in the recent years research. And next week we're gonna cover some applications and use cases based on those approaches we learned. Okay, especially we're gonna put more focus on these policy-based approaches. We're gonna learn some. I may pick up some applications based on these policy gradients, and yeah, to show how we can apply the policy gradients approaches in the real-world problems. Okay, that's all. Thank you. Thank you for your attention. And also, next week we'll have another quiz. Okay. Before the quiz, please review the content that we learned. Thank you.